All right, let's dive into the invisible, but believe me, incredibly powerful world of chemical reactions. We're going to pull back the curtain on the science that explains how pretty much everything around us changes, one tiny atom at a time.
So here's a fun question for you. What could possibly connect a rusty old car, a delicious cake baking in the oven, and your body breaking down your lunch? It kind of sounds like a riddle, right? But the answer is actually super simple. All of these things are powered by the exact same process, a special kind of dance that atoms are doing all around us, and yeah, even inside of us right this second.
So what is this atomic shuffle? Well, it's what we call a chemical reaction, and it is the engine of change in our universe. Seriously, it's happening constantly, everywhere, and the basic idea is a lot simpler than you might think.
Okay, so a chemical reaction isn't some kind of magic trick, it's just a reorganization. Think about it like this. The stuff you start with, we call those reactants. They're like a deck of cards. The reaction just shuffles that deck and boom, you end up with a totally new hand. We call that the products. The cards themselves, the atoms, they don't change, just how they're arranged.
And this Lego brick idea, it's the perfect way to think about it. During a reaction, you're not creating or destroying any atoms. Nope, they're just like Legos. You can take apart a Lego house and use those exact same bricks to build a spaceship. All the fundamental pieces are still there. They've just snapped together in new ways to create something completely different.
So, if atoms are like Lego bricks, what's the click that holds them together? How do they actually form these new shapes and structures? Well, that click is what chemists call a chemical bond. It's literally the glue that holds our entire atomic world together.
And you've basically got two main flavors of this atomic glue. On one hand, you've got ionic bonds. Think of this as giving and taking. One atom actually hands over an electron to another one. This creates these charged particles called ions, and, well, opposites attract. Then you've got covalent bonds, where the motto is totally sharing is caring. Here, atoms decide to share electrons between them to stick together, forming really stable things called molecules.
Okay, so we know reactions are all about rearranging atoms, and we know that bonds are the glue. But is there any rhyme or reason to it? Do these rearrangements follow any kind of pattern? Oh, they absolutely do. Let's look at the four main recipes, or types of reactions that you see over and over again.
This table lays it all out, and honestly, the best way to think about them is like dance moves. A combination reaction, that's when two single dancers, A and B, come together to form a pair, AB. Decomposition is just the opposite. A pair, AB, decides to break up and go solo. Displacement is where it gets interesting. It's when a new dancer, A, cuts in and steals a partner from B. And finally, double displacement is when two pairs on the dance floor, AB and CD, just decide to swap partners.
Let's zoom in on one of those dance moves for a sec. Decomposition. What makes something break apart? Well, as you can see, there are three main triggers. You can use heat, like when you bake limestone. You can use electricity to split something stable, like water, H2O, back into hydrogen and oxygen. Or you can even use light. That's actually how the compound silver chloride worked in old-school photography.
This brings up a really fascinating question about those displacement reactions, the ones where an element cuts in. Why does that even happen? Is it just random? Why is it that some metals can just swoop in and steal a partner from another one, but it doesn't work the other way around?
Well, the secret is a kind of chemical hierarchy called the activity series. You can think of it as a ranked list of how reactive different metals are. It's pretty simple. Any metal that's higher on this list can kick any metal below it out of a compound. So because iron, or Fe, is higher on the list than copper, Cu, it can easily waltz in and take its place. It's the chemical pecking order, plain and simple.
But wait, there's more to the story. Reactions aren't just about swapping atoms based on a list. To really get the full picture, you have to add a couple more ingredients to the recipe: energy and speed. And sometimes you even have to account for a little outside help from a sidekick. Okay, this is a really crucial point about energy. Every single reaction either gives off energy or it sucks energy in. The ones that give off heat, like burning fuel, are called exothermic. They feel warm. The ones that have to absorb heat from their surroundings are called endothermic, and they actually make things feel cold, kind of like one of those instant ice packs.
And what about speed? Some reactions, like rust, take forever. Others are instantaneous. Well, to speed things up, chemists can use something called a catalyst.
It's like a coach for the atoms, showing them a shortcut or a faster way to react, but without ever getting in the game itself. When it's all over, the catalyst is still there, completely unchanged.
So why does any of this matter, right? Why should you care about combination, or decomposition, or exothermic reactions? Because this isn't just stuff that happens in a lab. This is happening all around you, all the time, solving real problems in your daily life.
Let's look at one super important type of double displacement reaction. It's called neutralization. And the rule is so simple, but so powerful. When you mix an acid with a base, they cancel each other out. And what do you get? A neutral salt and plain old water. This simple recipe has huge real-world uses.
And you see this in action all the time. Got heartburn from too much stomach acid? You take an antacid, which is a base, to neutralize it. If a farmer's soil is too acidic for their crops to grow, they'll add lime, which is a base, to balance things out. See? This is chemistry at work, solving very common, everyday problems. So, there you have it. The world is basically one giant chemistry set. From the bonds that hold everything together to the reactions that are constantly changing it all. You now know the fundamental recipes. So the real question is, as you go about your day, what new chemical reactions are you going to start seeing, cooking up all around you?